All right, today we're tackling problem 1.190 from the famous Irodov collection. Now this one's a classic. It looks pretty simple on the surface, but it's got this weird twist that reveals something fascinating about a force that isn't even, well, real. So let's dive into the world of rotating reference frames.
So this is the big question at the heart of the problem. How can a force that physicists literally call fictitious, meaning it's not a real physical interaction between objects, somehow produce something very real and very measurable, like angular momentum? I mean, it sounds like a contradiction, right? And honestly, this is where a lot of people get stuck. But don't worry, we're going to unravel it together.
Okay, first things first. Let's get the lay of the land and set up the exact problem we're going to solve. It all starts with a simple spinning disk, but as you're about to see, the physics is anything but simple.
Okay, so here's the problem word for word from Irodov. We've got a disk, it's spinning at a constant speed omega, then, right at time zero, a particle gets shot out from the very center with a starting velocity of v0. The key part of the question, the part you have to really pay attention to, is this. We need to find the angular momentum from the point of view of someone on the disk, not from our view standing still, but from the rotating frame itself.
Now, if you're just standing still watching this whole thing happen, what we call the lab frame, the motion is super simple. The particle just moves in a perfectly straight line straight out from the middle. No drama, no curves, just a straight shot.
And this is where things get weird. In that lab frame, the particle's direction of motion is always pointed away from the center, right? Well, that means its velocity vector is always parallel to its position vector. And if you remember your physics, angular momentum is calculated with a cross product, r cross p. When two vectors are parallel, their cross product is zero, always. So, in the lab frame, the angular momentum is zero. So how on earth can it suddenly appear in the disk's frame? Where does it come from?
Okay, to crack this, we've got to step into the slightly bizarre world of rotating reference frames. It turns out, the laws of physics can look really different depending on your point of view.
So we have two different perspectives to deal with. The first is the inertial lab frame. That's where, good old F equals ma works perfectly and everything behaves as you'd expect. But the disk's frame is non-inertial because it's always rotating, which is a form of acceleration. To make Newton's laws work in that frame, we have to kind of invent these extra forces to account for the weird motions we see. We call them fictitious forces.
And the main culprit, the star of our show, is one of these fictitious forces you've probably heard of, the Coriolis force. It's this ghost force that seems to push on anything that's moving, but only when you're watching from inside a rotating system.
Okay, picture this. You're on a spinning merry-go-round. You try to throw a ball in a straight line to your friend who's on the other side. From your perspective, it looks like the ball mysteriously curves away from them. It's as if some invisible force pushed it sideways. But for someone watching from the ground, the ball flew perfectly straight. It was your friend who rotated away from the ball's path. That invisible push you saw? That's the Coriolis effect.
Okay, with that idea in our back pocket, let's get back to the math. It's time to describe the particle's motion from both points of view, starting with the easy one.
All right, let's start with the lab frame. We can just decide to line up the initial velocity with our x-axis to make things simple. So the position at any time t is just its speed, v0, times time, all in the x direction, or I. Nice and simple.
Okay, now for the tricky part. We need to translate that simple straight-line motion into the language of the spinning disk. Just imagine the x and y axes painted on the disk, we'll call them x prime and y prime, are spinning around. The angle they've rotated at any time t is just omega times t. So, we use the standard equations for rotating coordinates, and we get these expressions for the particle's position as seen from the disk.
And what does this math actually mean? It means that if you were standing on that disk, you wouldn't see a straight line at all. You'd see the particle trace out this amazing outward spiral. That simple, boring straight line has transformed into a beautiful, complex curve just by changing our point of view.
So to get angular momentum, we need two things, position and velocity. We've got the position, now let's find the velocity. All we have to do is take the time derivative of our x prime and y prime position coordinates. Yeah, it involves using the product rule from calculus, but it's a totally standard step to get us to the velocity. Okay, we've got all the pieces of the puzzle now. We have the position vector and the velocity vector, both in the disk's frame. Let's put them together and finally calculate that angular momentum. Right? It's time to get our hands dirty with the calculation. Remember, angular momentum is r cross p, or in our case, m times r prime cross v prime. To keep things from getting messy, here are the components of our position and velocity vectors all laid out. Just take a look at what we're working with here before we plug them in.
So now we just plug everything into the cross-product formula. Since our vectors are just in the xy plane, the formula simplifies to this: x prime times vy prime minus y prime times vx prime. And notice, the result is going to be pointing in the k prime direction. That's straight up or down perpendicular to the disk.
And bam! This is the magic moment. When you substitute all those terms into the formula and you grind through the algebra, something amazing happens. A whole bunch of sine and cosine terms cancel out, thanks to our old friend sine squared plus cosine squared equals 1. And we're left with this beautifully simple result. The angular momentum is not zero. It's real, it's pointing downwards, and it gets stronger and stronger over time, growing with t squared.
So we've got the angular momentum. That's a huge part of the problem. But we're not quite done. Now we need to make the final connection and prove that this angular momentum is all thanks to the Coriolis force.
You know, this result should make you pause and ask a question. One of the fundamental laws of mechanics is that if you have a changing angular momentum, you must have a torque. But wait a second. The problem says the disk is smooth. There are no real forces pushing the particle sideways. So where is the torque coming from? This is where it all comes together. We can prove without a doubt that the Coriolis force is our culprit. First, we write down the formula for the Coriolis force itself. Next, we calculate the torque it creates by taking its cross product with the position vector r prime. And when we do the math, guess what we find? The torque from the Coriolis force is exactly equal to the rate of change of the angular momentum we found earlier. The physics works out perfectly.
So what are the big ideas to take away from all this? First, and most obviously, motion is relative. A straight line in one frame is a spiral in another. Second, to make sense of the world from a rotating point of view, you have to include these so-called fictitious forces. And finally, and this is the coolest part, these ghost forces can produce totally real, measurable effects like torque and angular momentum.
And that brings us to one last really cool thought. This whole principle isn't just for abstract physics problems on a little disk. It applies to the massive spinning object we're all living on right now, the Earth. That same Coriolis force is what causes hurricanes to spin and what drives large-scale ocean currents. A fictitious force with very, very real consequences for all of us.